Hot dry rock geothermal energy, America's best kept energy secret. An EnviroVideo special next. Hello, I'm Carl Grossman. Hot dry rock geothermal energy, a tremendous energy resource. Let's go to a videotape. An energy-free lunch, all the energy we'd ever need, and it's just under the ground. No environmental cost, no problems of safety, no waste. Energy both virtually endless and cost competitive, say its proponents. It's called hot dry rock geothermal energy.
Hot dry rock has an almost unlimited potential to supply all the energy needs of the United States and indeed the world. There's a tremendous amount of energy right beneath our feet at depths that we can reach with current drilling technology.
Environmentalists are excited by the prospects.
Well, hot dry rock is so good that sometimes it almost seems too good to be true, but it is true.
It's a simple process that's been shown at Los Alamos to work and work well. 2 to 6 miles under the Earth's surface, it's hot, real hot. Just drill down, and oil rigs, many of which are inactive these days, can do it, and position 2 pipes. Into one, an injection pipe, water is pumped. Once it hits the hot rock below, the water boils, and presto, comes up the other pipe as superheated water ready to be flashed to steam. The steam can be used for heating or to turn a turbine and generate electricity and send to power a city.
We know how to do the technology, but we don't really have sufficient funds to implement it at this time.
In the 1970s at Fenton Hill, New Mexico, Los Alamos scientists set up a hot dry rock system which has been successfully operating ever since, demonstrating that power can easily be produced through the process. The environmental downsides?
None that we're aware of, and we've investigated the process for almost 20 years now.
In fact, a well-run hot dry rock energy recovery system, properly run, has virtually no environmental harm of any type, and therefore it's almost a free lunch.
And the energy potential is stupendous.
In analyzing how much heat is trapped in the first 6 miles of rock below our feet, the numbers turn out to be stupendous. If only 10% of it is tapped, we could run the country for tens of thousands of years at today's consumption levels.
But the U.S. has been slow to implement this new energy process it initiated. The U.S. government invested as much as $20 million a year in hot dry rock geothermal technology in the mid-1970s, but under the Reagan and Bush administrations, the budget kept falling. The Clinton administration was left with the lowest development budget since 1973 for what could be America's best-kept energy secret.
Millions of human beings on this planet, their lives, whether they're in the auto business or the energy business or whatever, are all hooked to the existing energy source, which is oil, coal and oil. And it's hard to change the ship of state. Everybody just keeps doing what they're doing because they're comfortable at it.
Meanwhile, other nations are moving rapidly to develop the technology the U.S. initiated, including Japan and Germany, which joined with the U.S. in the early work at Los Alamos. Next year, in fact, Germany, France, and Britain will be joining together in a $300 million program to expand hot dry rock development already underway in Europe. Japan now has 3 sites in a multi-million-dollar hot dry rock program. And would you believe, since that tape was made, the hot dry rock program at Los Alamos National Laboratory has been decimated, virtually zeroed out by the Clinton administration in mid-1996. With me is Dr. Jefferson Tester. He is the director of the Energy Laboratory at the Massachusetts Institute of Technology. He's long studied hot dry rock. Dr. Tester, the potential of hot dry rock seems enormous. Are we missing the energy boat by this country not taking advantage of it?
The potential of the resource is indeed large, Carl, and as you know, and I think as the tape points out, in order to make this work requires sort of the same characteristics as mining. In this case, we're mining heat from the earth, so there are certain important both technical and economic aspects that have to be looked at. But if we look at just the potential and the ability to provide either heat or electric power continuously, it stacks up quite nicely against some of the other options that are out there.
Now here's a technology that was developed by the government essentially at Los Alamos. The term that's used these days for getting technologies developed at various national labs out on the shelf, in the street, and what have you, is technology transfer.
Right.
What do you think it'll take to get hot, dry rock transferred?
Well, I think one of the steps that that has been discussed over the years, this has been a technology, in a sense, that's been developing over about 20 years or so now, and to some extent it had a rapid sort of growth period during the same period of time when energy prices were high, where there was much more public concern about the availability of inexpensive energy. And after that period, which was roughly around 1980 or so, in the early 1980s, the funding sort of started to tail off, not just for hot dry rock, but for all sort of advanced or new energy systems, partly driven by a perceived need that was disappearing, and also other issues within the way in which the government and the Department of Energy were spending funds. But I think that what it's going to take is clearly not just one experiment. I mean, the Fenton Hill experiment is indeed that, and I think it's a very positive story. It needs to be carefully looked at in terms of the impact that it's going to have in terms of multi-plant development across the country or in the rest of the world. So something besides a field test at Fenton Hill will probably be required. When I look at the resource across the country, there are areas which we call high grade, which have high thermal gradients, high geothermal gradients, where we don't have to drill so far to get to that resource. Those represent kind of one class of systems. Frequently, they're associated with hydrothermal type activity where maybe millions of years ago or tens of thousands of years ago there was volcanic activity in the area, so that they have a higher heat flow coming up from the center of the earth in that local region, and that's more economically attractive. It would be the same thing as drilling for oil in Saudi Arabia, where it's rather easy to extract oil from shallow reservoirs as opposed to deep continental drilling in the U.S. But there's another resource, and this is really the one that, if in order to make what I call universal heat mining, in order to have something that we could apply ubiquitously across the globe, we're going to have to go after the low-grade resource as well, which means lower gradients and deeper drilling. So what my hope would be is that in this opportunity to sort of transfer the technology, that we would look at different classes of geologic systems, high-grade ones like Fenton Hill, perhaps even within the margins of an existing hydrothermal field, and moderate to lower grade areas which are cited not necessarily because of their geothermal potential, but more where the end use need is. So we go to a city, or we go to a small college or something like that, and view this as an opportunity to prove that we can universally mine heat, and whether that could be done economically. So I think it would take several demonstrations around the country and perhaps worldwide, and this is, of course, an important issue because of the cost associated with these. So,
Jefferson Tester of the MIT Energy Laboratory. If you'd like any more information, here's the address of the MIT Energy Laboratory. Meanwhile, you might want to write to the U.S. Department of Energy in Washington, D.C., to your representative, to your senator, and ask what is going on or is not going on with America's best-kept energy secret. Perhaps after this show it might be a little less a secret: hot, dry rock, geothermal energy. I'm Carl Grossman. Thanks for watching.